Yes. Okay. So yeah, so let me first introduce Abhinav. So Abhinav and I shared, actually we joined both University of Utah at 2018, and I guess we met at the orientation, a department orientation when we were here. And Abhinav did his, I think, masters from IIT Bombay, and then he spent some time in Xerox research in India, where he works on few cool problems like I remember license plate detection, and they were practically also used, and many patents were filed on them. And then he was here for University of Utah for I think 2 years, working with Professor Kumar Ramalingam, on face and object detection algorithms and all. And then I think he recently got transferred, I think not recently, like 1 or 2 years now, in Michigan State University. I think he's working with Shiling, if I pronounce it right,
Yeah, it's Professor Xiaoming Lu.
Charming Lu. And
Yeah.
he also has stint at I think Merle Vision Lab for working on interesting problem in vision. And I think in 2020 he will be he is going for summer at Facebook AI research for computer vision problems and all. Yeah, so before anything else, I'll leave it to Abhinav to present. And I think these are the work he did for CVPR 19 and 20, I think. So it's good to have some vision people also present. I was looking for some good talks. So hand over to Abhinav. Abhinav, thanks for doing this at short notice, and thanks everyone for joining the seminar. That's all. Thank you.
Yeah. Thank you, Vivek, for the nice introduction. And today we'll be talking about mathematical modeling for landmark and 3D object detection. So I have I have kept the mathematical modeling in a little bit, I would say, like downgraded in flavor, more or less primarily because I want everyone to basically get a feel of what we have been doing here. So let's get started. So computer vision models have been achieved several state-of-the-art performance on tasks such as like facial landmark detection and also on monocular 3D object detections. So it's not only limited to classification or semantic segmentations. They have showed impressive results on these tasks as well. But the issues, with the primary issue with these computer vision models are first of all, they suffer from a couple of a number of issues. And the first of the issue, which I find it really intriguing, is like they are not mathematically principled. So what this means is you could find some elegant mathematical modeling and even push the performance even further. The second important issue which these models which would suffer, as we'll see in the talk, is they also use some of the non-differentiable modules primarily in inference. And these modules are basically not a part of training anymore. So that creates a mismatch between training and inference pipelines. And the next significant drawback is a couple of these models are non-interpretable as well. So I'll first start with the first task, which is facial landmark detection. This is also known as by the name face alignment in literature. So this is primarily a CVPR 2020 work, which was done when I was a summer intern at Mitsubishi Electric Labs in Boston. And here are all my collaborators. So this is a joint work with Tim, Wengshuan, Yi, Mike, Anup, Toshi, my advisor Xiaoming Lu, and also Chen Peng from NYU. So what is facial landmark detection? So the idea is to feed images to a network, and the output should be certain landmarks on the faces. So basically, this is a regression task. And the job of this network, like what you see, is a stacked U network, or it's also known as stacked hourglass network, is to predict the precise locations of where these landmarks are. So the number of landmarks could be different depending on the data set. But the overall, the idea of this task is to predict where these landmarks are. So these models, as you could see, are actually trained not directly on the landmarks. They are actually trained with a loss function between a ground truth heat map and a predicted heat map. So I'll talk about what these heat maps are. So for example, consider this as a face, and this is the position of ground truth landmarks on the faces. So the ground truth heat map is basically generated by placing a symmetric Gaussian on the top of it. So basically this everything is zeros, and for this landmark you see we have been placing a small symmetric Gaussian on top of it. For the other one it would look similar to this. So the major issue with like this heat map based prediction is offers a couple of advantages. For example, like the convergence is faster and all those stuff, but the issue with these heat map based approaches is like it's poorly suited for uncertainty prediction. So for example, like you every time you pass on a test image through a network, you'll always land up with some kind of a Gaussian centered heat map, which doesn't show any idea about like is the network sure about the prediction or not. And the second issue which I would like to show up is like how do you get the final landmark from these heat maps. So what you do is like you do an argmax over this prediction, or basically like where is the brightest spot in the whole heat map. So that's then argmax, and everyone knows like argmax is a non-differentiable operation. So that hinders end-to-end training. And the second important drawback with using argmax is like it doesn't allow sub-pixel level accuracy. So basically the network can only predict accurate up to a certain pixel, whereas the landmarks could actually go within the 2 pixels as well. The next important issue is like we saw that these were trained with L2 loss. Yeah, go ahead.
So are these landmark, like how many are these are generally in a phase, like these are sparse or not? Like if they're sparse, we can use sparse max or something. Like is there any intuition on those, like prior aspect of these landmarks? Like
so in general, like it depends on the data set. So for example, what I'm showing here is an example image from 300W data set, which has 68 landmarks per phase. There are other data sets which have 19 landmarks, 98 landmarks, and we'll be running this algorithm on all those data sets. So just hold on for a second. I'll show you all the qualitative results. You will have full of faces. Don't worry.
Okay. Thank you.
So, and yes, feel free to stop me. I'm not able to see the chat window here. So if there's a question, please feel free to stop me, and I'll try answering your question at that moment itself. So the other issue with the facial landmark detection is they use a symmetric MSE for training, and MSE, or the mean squared loss, is like equally weighted for every landmark. Now this happens to be a problem again because every landmark has a different labeling error. So for example, this is a typical phase from another data set, and we have like the so authors like Sagunas et al. Have plotted like how does the covariance look like for like if you label these points on the faces of people, they could get different amount of labeling uncertainty which could show up. For example, the uncertainty is large along the chin, which is expected, whereas for the uncertainty is actually small for areas such as eyes, nose, and particularly around the mouth. So the MSE ignores this prior at all because it doesn't have any idea of like how this uncertainty would look like. So what would ideally want is this MSE should be weighted by what is the uncertainty for these landmarks, or at least the labeling uncertainty for these landmarks. So that is another issue which needs to be taken care of. So in summary, like these are the issues with the current or the landmark detection approaches. For example, the training is not end-to-end. The second thing is like they do not report uncertainty because obviously like if they are predicting a symmetric Gaussian for every landmark, you cannot say like which landmark it is sure of or it's not. And this visibility arises when the face turns. I'll be showing some examples later, but for now, like you can safely assume that like some of the landmarks might become invisible if you turn your face like this. So that is also not modeled in these models. And finally, the loss actually inherently is not very mathematically principled, and it at all ignores the uncertainty of the landmark. So we'll be tackling each of these problems one by one. So hold on a second. So our prediction would be something like this. We'll not only predict the position, we'll also predict uncertainty associated with this prediction. And in addition, we'll also predict whether these landmarks are visible or not. So we will be predicting what is known as location, uncertainty, and visibility as well. So what is that? That's what makes it location uncertainty of visibility, and that's what makes it a lovely phase alignment. So how do we do that? So the first issue was the location was not location prediction was not end to end. So we use a standard Gumbel softmax kind of idea, and we use a ReLU spatial mean of the ReLU heat map. So that gives you sub-pixel level prediction. The second uncertainty is achieved by using a small network. It's basically a single layer, linear, fully connected layer, and it's actually shared across all the units. So it's the arrow here, which says that it's shared across all these units. The visibility is also estimated by a small network attached to the bottleneck of each unit. And finally, the loss, which was very, very, like I would say, like not so mathematically principled, we optimize it using a negative log likelihood. So how do we land up with this? So let's talk about like what are the ground truths and the prediction. So the ground truth and prediction we keep it as a mixed random variable. And the regression part basically takes care of the location and the uncertainty part, whereas the classification part actually takes care of the visibility. So mind you, the ground truth doesn't contain the explicit uncertainty part. Ground truth only has the location and the visibility, whereas prediction contains location, uncertainty, and visibility. So there are three things which are predicted about each of the landmarks. And what we show is like the KL divergence between two mixed random variables. And for the prediction is actually location, uncertainty, or visibility, while the ground truth is more or less like a Dirac delta function for the regression. And that reduces to a negative log likelihood, and it elegantly decomposes into two terms, which is what is known as classification and regression loss. So someone familiar with with object detection might find it very intuitive, because classification plus regression is used in object detection as well. So where does this lie in the literature? So there was an earlier result from 2018, which showed that like if you do a KL divergence between two continuous random variables, that reduces to a regression loss. So if you use a mixed random variable, what we show is like this reduces to a classification plus a regression loss. So it's a slight upgradation of that. So how does the loss become? Because the regression point is like, I have not talked about what likelihood did I use for the part. So we use a Laplacian likelihood, which was formed is this one. And when you, the loss function that we use for optimization of this whole network has a classification part, which is like this. So V is the ground truth labels, whereas the V overhead arrow one is the predicted one. And this, the second part is what is the regression, and this takes care of like the prediction and the predicted uncertainty. So there are two terms for that as well. And you could see that this is getting weighed. This is not a standard MSE. It's a Mahalanobis distance kind of idea, which the uncertainty weighing the MSE term. So why did we use Laplacian likelihood? The reason was like we tried even multivariate Gaussian, and the multivariate Gaussian was not able to get better log likelihood. So we stick with Laplacian likelihood. So most of the phase alignment datasets actually do not contain an explicit visibility label. So we also provided one new labeling scheme of an existing AFLW dataset, and which is what is called Merle reorientation of AFLW with visibility. So there are visibility labels. And what do you mean by visibility labels? So you could, for example, if there are faces get turned, so there are some of the landmarks which are not getting visible. So that's what I'm showing it by black. And the green ones are like which are fully unoccluded, while the red ones are one which are externally occluded by somewhat like by an external object, maybe hair, maybe a cap, maybe a glasses, or so on. So what are the evaluation metrics for these tasks? The evaluation matrix happens to be the normalized mean error, which is like the prediction between, like the error between the prediction and the ground truth. And D happens to be a normalization term. So it could be, there are a couple of normalization terms in the literature. So one is called interocular distance, which is the outer corner of the two eyes. This is also what is known as box distance, which is the, when you take the box and choose the geometric mean, that's also one of the like normalization terms. And NP is like you average it over across the landmarks. So This depends on the data set you use. So it could be 68, 19, or 98 landmarks. And the second, so this has to be lower the better. So because you want the error should be smaller. Whereas for the area under the curve this metric should be higher the better.
So how do you basically say if your uncertainty is good? Because this evaluation only take mean in consideration, like.
Yes. So we'll use there's no technically way to like these metrics do not evaluate the uncertainty, but uncertainty you could evaluate it if you have the expected value of the squared error and you compare it with the uncertainty. So I'll show some plots on the correlation between that. So first of all, I'll talk, because the LUVLI paper is about location, uncertainty, and visibility. So I'll first talk about the location. So that's why I'm talking about location here. So we tested it almost on I think 9 data sets, and on every data set like we get some state of the art results which hold even till now, even after 2 years. So it's a miracle sometimes, but I'm showing some of these results and in different poses of the face. The uncertainty one which you just asked, so it's like I predicted uncertainty. So this is the predicted. So the uncertainty will be in general a 2x2 matrix which has 3 degrees of freedom because the covariance is like symmetric. So you could plot the residual sigma which you can obtain by like the mean minus the ground truth, and you can also plot the predicted sigma which is like you can obtain, and it shows pretty good correlation with in almost all the 3 axes. So, and the important thing to notice is like the xx1, which is like only along the x direction, that's only positive, which is expected because that's a variance term technically. Whereas the covariance term, which is sigma xy, that's also negative. You could see like it goes towards the negative as well. So they are very, very like correlated, which is a good news. So that's the only way we are able to evaluate the uncertainty. I do not have any other metric to evaluate it. So
the ground truth have those uncertainty? How
no, the ground truth doesn't have it uncertainty.
Okay, so the residual and the predicted one.
Yeah. So the residual has mean minus ground truth. So you could take the expectation squared. So that mean and ground truth, you have that.
Okay.
So that gives you an idea of that.
And then you take, okay, I got the point. Okay, good.
So, okay, so we talked about like how human labelers predict, like they have some labeling errors as well. So how does this compare with our prediction? So I show it to you for eyes, it is very similar for 3 human labelers. For the chin, I think it should also be similar, but it's not exactly the same. You could see there are certain differences. And in regions such as this, like at least on the tip of the chin, they are not that similar. But overall, there seems to be quite similar in nature. It's not like it's, so the uncertainty which is being predicted does look similar to what a human labelers would give. So finally, the third part, which is like the visibility part, and I talked about like there will be some points which will not be visible on that side of the face. So for them, the visibility should be small, which are called as self-occluded points. And as expected, their visibility is small, like this is close to 0. Whereas for unoccluded and the occluded ones, it's close to 1, which is what we expected. So that's also good. So finally, some qualitative results for Vivek, and he wanted some. So this is a data set which has on 68 landmarks. So there'll be 68 points everywhere. And this doesn't contain any profile faces. So you'll not see any landmarks getting invisible here. Whereas other data sets, for example, MERRAV has a visibility label and it has some profile faces. So you could see that some of the landmarks are not visible at all because they are considered invisible now. This is a 19-point landmark data sets. So that also gives us some idea of uncertainty. WFLW is a 98-point based method. So that also gives you some, so there are more dense points here compared to here. You could visually see that. So finally, okay, fine, this looks pretty good on data set. So does it work really? So that's the first thing. And I have some demo video, which was actually prepared in Vivek's lab when Vivek was not here. So the person in the demo was Maitre, because Vivek was not present in the lab that day. So I'll just try playing it. And if he turns his faces, and this image is not present in the data set at all. It's like we trained it on MERLab and just tried placing it. So you could see that if the faces turn, like those points start becoming invisible. And when it again shows up, like becomes a frontal face, then you could see that uh, those landmarks reappear. Okay, so this is the summary of the first part of the talk, which is like we jointly estimate location, uncertainty, and visibility. There are some SOTA results on multiple data sets. And finally, the uncertainty is similar to human labelers. The demo and the code, everything is public. Please feel free to try it out, or if you have any issues, like just open an issue on GitHub and I'll be more than happy to answer it. So, okay, so let's, how much are we on time? I think we are pretty much on time. So let's talk about the second half of the talk, which is like also a regression task, but it's a different module this altogether, and it's more or less related to autonomous driving application, which I'm currently working on. So the task which I'll be talking about is monocular 3D object detection. And this is a joint work, is a last year CVPR work, and it's a joint work with Gary Brazil and my advisor Xiaoming Lu, who both are at MSU. Gary is now at FAIR, but by the time it was published, he was here. So a 3D object detection involves predicting 3D boxes from a multimodal data, and it could happen like you could use either all the three data, or you could use only one of them. So each of the data point, like radar, LiDAR, or camera, comes with its own set of advantages and disadvantages. And in particularly, camera happens to be very good for object classification because it has the data density is particularly very good, and radar is quite sparse actually. Like you could not see like much radar data points, and it is quite noisy as well. LiDAR is pretty accurate, but the problem with LiDAR is like it requires very heavy processing, and it has a much more dense point cloud data. So monocular 3D object detection only involves like using one image at a time, like image from a single camera. It's actually quite simple, and it has a less memory footprint. So I'll show you a small demo of like how does like a 3D object detection look like. So this is the camera is actually mounted on an autonomous vehicle, and you should be able to see. And this is actually in the top view, which like where are the things in the top view. Okay, so monocular 3D object detection, despite being simple, comes with its own set of challenges. So for example, like the foremost challenge is like, it's not a well-posed problem. So there's a scale or a depth ambiguity in detecting 3D boxes from 2D input. And why does this happen? Because multiple 3D boxes could have the same 2D box in the image. So predicting, like inverting this back from like taking from 2D image to 3D, that suffers from a scale depth ambiguity. So that's a challenge in monocular 3D object detection. So let's talk about some object detection pipeline first. And in general, an object detection pipeline is typically composed of these modules, and the backbone is usually a standard CNN, maybe a ResNet or a DenseNet. There's three heads which are called as score, which is the quality of the box. There's also a head which predicts the 2D of 2D box, and there's also a head which predicts the 3D box. And in training, the losses are only applied before a module named NMS, which I'll briefly talk about now. So in general, like the prediction happens to be multiple boxes per object. For example, if you could see two cars here, so you don't get only two boxes, but you rather get multiple boxes for first car and multiple boxes for the second car. And there's a module which sits after this prediction, which is known as non-maximal suppression, which is the central focus of this work. what it does is like it removes the boxes which have like less scores or which are not of very good quality, and only make sure that there is only one 3D box per every object, so that the tracking is easier. And there are a lot of downstream tasks which depend on object detection. So if you put it more number of boxes per object, there could be an issue. So an immediate uh, like conclusion which you could draw from this figure is the training and inference are, there's a mismatch again. So the training is only on these dense boxes or the dense predictions, but the inference involves NMS, and NMS is not a part of the training at all. The second issue which happens because of this monocular 3D detection is because you are seeing the boxes in 2D, the classification score doesn't represent the 3D location score. So there could be some boxes, these two boxes have the same 2D box, if you could see from here, but their location in 3D might be very, very different. And the classification score is not able to basically say that like where this object could be in 3D. So there is best 3D localized box, which is could be in 3D, might not be chosen after NMS if you use a classification score at all. So what do we say? The easy solution, I think everyone could say that is like, why don't we pull NMS in training? If you pull NMS in training, the mismatch goes away, and possibly this score gets very well aligned to the 3D localization. So the central focus of this work was to make this NMS algorithm differentiable and pull this in training and make it end-to-end training and make it, and with the addition of what I would say, like keeping the groomed NMS interpretable. So that's the central focus of this work. And NMS is, I think, ubiquitous in almost every object detection pipeline. And this has been there for the past 50 to 60 years. So if something stays there for like more than 5 years, it's a big achievement, I would say, in the current deep learning era. But this has stayed as such, and people haven't tried much, at least to get us some kind of a mathematically principled NMS. So just to refresh, what does a non-maximal suppression does? You have a dense predictions for every object, and there will be some quality metrics, or basically the scores. And what you want to keep is like only one object, one box per every object, which could be like the best box, which is the highest score one. I only keep that, and the rest are thrown away. So that makes sure that you only get one box per object. So I'll just talk about like the classical NMS, and the classical NMS happens to be neither parallelizable nor differentiable. But what we propose is what is called groomed NMS. It's both parallelizable and differentiable. And the groomed NMS that I talk about will have a very clean mathematical expression with matrix operation. It's not like just stack some layers and assume that it will work like an NMS. So we'll use some mathematics here to get a clean expression, or at least a good approximation of what a classical NMS is. So a classical NMS, as you saw, it takes the scores and also the overlaps between the boxes into account, chooses the highest ranked box, and does a clustering, because you don't want to throw those boxes which are not overlapping with each other, and then rescores them. So basically keep only the highest ranked box as the same as whatever it was, and other boxes are suppressed to 0. Whereas because this argmax is non-differentiable, what we do is like we do a sorting. So sorting in descending order is equivalent to doing an argmax, because you could do that. And the rescoring module which we derive is a small matrix based, a very, very simple mathematical expression. And this makes the pipeline differentiable, because sorting is much easier to handle. And the rescoring, because it's now matrix based, you could actually differentiate it through the NMS. The grouping still, although in this NMS is non-differentiable even now. So the idea of NMS is like the score of a box with a high overlap with any other high scored box should be suppressed to 0. So this any you could think of as logical OR operation. And because the logical OR operation can be replaced by, I think this is a paper from Vivek's lab. So you could replace that like the OR operation by a corresponding sigma operation. And that makes it like, at least the logical operation goes away. And you could write this in a form of like a matrix expression, which is, I have just written this. This is for one of the boxes. I just wrote it for all of the boxes, and the pattern looks like S minus PR, which is still the issue with this is like it's non-linear because of this max, and this is recursive. So the R sits here as well, and R is here as well. So you could not use this to gain some kind of a clean layer. So what we do is we assume that the max is not present. For now, assume that the max was not present. So what you can do is like you can pull this PR toward that side to on the LHS, and that becomes an I plus P times R equal to S. And you could now use a matrix inverse, which is I plus P inverse S. And in general, like this is the inner expression is not bounded between 0 and 1, because this, after all, these are the scores after NMS. So that should still be bounded between 0 and 1. So I use a clamping operation on top of it, which is also a differentiable operation. So clamping is also a differentiable. So that still makes it differentiable. And the benefit of this expression is like now it's parallel and it's differentiable. And you could still rescore it compared to these two. But the job is still not done. This is actually quite slow, and we could have like a big matrices like this in general is around 3000 cross 3000, and that would make it terribly slow. So we use the second idea like of the grouping. So in general, like boxes only appear at the positions where the objects are. So you could run a grouping offline based on the overlaps, and you could split this P matrix into the groups of boxes. So that makes it like smaller, because now the groups only contain a few hundreds per object. It's not like a big thousands of. And the next idea that we use is like you could mask out one of the matrices, which is what a classical NMS does. So now this becomes a Frobenius matrix, because you only have one of the elements which are non-zeros, others are all zeros. So this inversion is now can be easily done by a simple subtraction operation, because this now becomes a Frobenius or a Gaussian transformation matrix. So this is what the final expression looks like. This is what we call it as a grouped mathematical differentiable NMS, and it only contains like a few subtraction, element-wise multiplication, and scoring. So the final layer looks like this. There is a sorting, and the expression what is I saw here, I have just put it here, and the grouping is still non-differentiable, but you could still differentiate through this NMS based on the scoring function R. So how do we get this the backward gradient here? So we use what is known as a loss function, which is our AP loss, and this is a ranking based loss. The vanilla AP loss actually treats boxes for all image equally. We do it in an image wise fashion. So for example, if the boxes are correctly ranked in one of the image, but not in the second, we only update the scores of the second box. So this ensures that like you are only updating the relevant scores of the relevant images. So how does the gradient from this groomed NMS and AP loss look like? So for example purposes, I'll only show it the example that for the group 1, the similar things carry for the group 2 as well. So the top box would be sitting with the highest score. So that is like the red one. And there will be other boxes which will get suppressed right after the NMS. But the best localized box might not be at the top. And in that case, if you use this kind of loss, what it says like it will decrease the score of the top box, whereas it will increase the score of the best box. So that like this, if this box goes above this red one, then after NMS, the green box will be there, and which is what we want. And in the second case, like it would happen that that top box is the best localized box in that case. So in that case, we do not change anything. We just keep it as it is. So this is what a groomed NMS and an AP loss would do. So we did some experiments on Kitty, and this is actually an autonomous driving data set. A couple of splits are available. So we tested it on all 3 splits, and the matrix happens to be an average precision at 2 IOU thresholds. So this is on the Kitty server, which is like the test labels are not known. So one has to train a model and then upload to the server to get the results. So interestingly, we at that time, we outperformed all the image-based methods. And this is the last one is a video-based methods. And we could see that its accuracy now becomes even closer to the video-based method. And sometimes it even surpasses it on some of the metrics as well. And this method is simply an image-based. This doesn't use video at all. And I talked about like the correlation between box score and 3D localization. So that also gets improved. It's even better than a video-based method, which is 0.338. We are still better than that. and it outperforms a video image-based method and like a 3D object detection image-based and a video method-based method as well. So now I want to make sure that everything is in place, saying that like the NMS expression that we came up with is actually an NMS. So what we did was we took the original the baseline model and our model and changed the NMS with a couple of different NMS. So this is the C stands for the classical NMS, and we use only change this in inference. So what we see is like it doesn't change the performance by much, which means that the groomed NMS is a pretty good approximation of the classical NMS. And this happens with the second model as well. You could see that the performance is almost like there are only changes in the last second digit of decimal. So that means the expression that we landed up is actually a pretty good approximation of the classical NMS. So these are some of the qualitative results on Kitty dataset. These are on the categories of cars. And in general, what we see is like the proposed model is better than the baseline. And I'll also show some demo video, like I think, yeah, this is at twice the frame rate. And you could see this is on the from the top. How does this look like? Okay, so yeah, that brings us to the end of this talk. I think I'm almost perfectly on time. So yeah, so the code demo and everything is all publicly available. Feel free to try it. And this was actually supported by Ford and Army Research Office. And yeah, so these are the two works I basically talked about. Both are basically related to classification plus regression setting. One is for faces and one is for 3D object detection. So yeah, so thank you.
Great. Thanks, speaker, for the wonderful talk. Anyone has any questions or anything? By the way, Abhinav, did you try to sell it to some company and earn money?
Yeah, so this is actually so the Ford. So Ford actually so MSU filed a patent on this work, right? And Ford has actually is interested to get this, like purchase this. So we haven't tried it explicitly because this is the property of MSU, but MSU is trying to sell it.
Makes sense.
Yeah.
I think Professor Jeff has a question.
Yeah. So really nice work. So I was wondering on the first subpart where you're doing the face recognition, it looked like most of the example faces were of like mostly pretty beautiful people, right?
Okay.
And like mostly like Caucasian people,
Okay.
not everyone that dates that. Do you have, so like, I know these are like the standard benchmarks in this area, but have you thought about and looked into how this extends, outside of this, like the properties of the training set to like more diverse faces?
Unfortunately, no. But I have I know that there are like the problems with face literature is like it works pretty well for some of the Caucasian faces and might not work for other races as well. So there are certain bias issues which show up there. But unfortunately, we didn't study this because the primary issue with like these data sets are like nobody is willing to release their own, like publicly release the internal data sets for benchmarking. So maybe someone else might need to do, but we didn't do. And the data sets do not provide an explicit label of the races in these data sets.
Yeah, was there not a so I had hit, you know, a little bit outside my domain, but
Yeah.
was there not a like diverse data set released a year or two ago by Joy? I forget her last name, but she's worked a lot on these fairness issues.
Okay.
So it might be, you know, I know this now. This was a work you had done in the past, but
Yes.
you know, I would. It'd be something I'd be interested to see. If I mean, the general principle of it is great, right? It's identifying features I think that are common to faces. But the question is, if you know, you have some data sets in here, like the in the bottom, in the middle of with darker skin tones, and it seems like it's still working here. So I'm curious, like if because of the principles behind it, if you believe it should transfer to these these other issues, or if you foresee there are some specific challenges that you would have when you are leaving these data sets towards you know, like other still relevant data sets.
Yes, I think that would definitely be a worthwhile area to explore, I would say. Unfortunately, at least for the MERL-RAV dataset, which is basically a re-annotation of AFLW19, it still doesn't have a race kind of label. So someone has to label it out like these are pretty Caucasian faces, these are some Asian faces, and that way. And then we can study at least some idea of like how the model gets like performing there. But right now it's not there in any of those. So, and I'm not aware if someone has followed up on these works along that demographic kind of study. So, yeah, maybe it's an interesting future work for sure, I would say.
Yeah, so there was like a diverse faces data released in this was a couple of years ago, right? That this work. Yeah, so it was released in 2019.
Okay.
Right. So there's like a diverse faces data set released by IBM, for instance, I found.
Okay.
And I'm not sure if this is the one I had in mind, but yeah, if you work more in this area, I would suggest to kind of, you know, keep these things in mind.
Yes, sure. I think that's a very, very nice suggestion. So just
Abhinav, maybe you can also take this data set, and if you get like maybe get it annotated by someone, like because these data has facial location mark, maybe those data set don't have. So that could also be one of the nice idea, and show that your model work really well for all of them. That will bring really good power to it. Like, yeah, okay, this worked very well across diversity.
yeah,
So you can take these existing and maybe label them. But I don't know how you'll do that and how you'll get funding and all. But yeah, there are some ways. If you can even take these data set and then also release them for future people, so that when anybody build a algorithm, they can also use it. I think that's a very nice suggestion.
Yeah, I think even the point of labeling them is even a little bit like problematic if you don't know how these people actually, what their own representation is. You're kind of just guessing at that point, and that leads to other issues. But I think this data set is meant to try and capture a diverse set of types of faces, the one that you put in the link Vivek, and you know, without having, I don't know if it has explicit labels on the types of people that are in it, but it should be maybe hopefully more representative of the population as a whole.
Yeah, it doesn't have the gender labels. Neither this or this. Even I think none of these have like a gender or a race kind of labels. So someone has to annotate it, like to get at least some idea.
Well, so I don't know if you need to say, well, it works this well on this gender or in this race, but if your data set actually is representative of the population and it does well on that data set as a whole, then you'd hope that it's going to do generalized to the whole population, as opposed to just, you know, when you have an elevator that opens the door when it sees faces, it doesn't just open the door if it sees a very beautiful face, but or a very Caucasian face, but it opens the door for for anyone. Right. So those are sort of issues that have actually happened in the real world with when these have been deployed. But so I mean, I understand you did this work before this other data set came out, or so that's understandable. But
Anyone else? Any questions? Yes. So I have a general question, Abhinav. So you
Yeah.
were now working on like this autonomous driving vehicles and these things. So what are you think is the next challenges around, like, or what are the things where more improvements need to be done so that we soon start seeing vehicles where we just sit and nobody drives it, or like where people sit on the first seat is not driving seat but it's general seat, like anything. So what do you think are the high level challenges which is there?
So I'm still working on 3D object detection, and I specifically focus on monocular 3D object detection. I don't focus on radar, although I'm still like I'm a bit scratching the surface of radar-based detection as well. But my primary work is right now on monocular 3D object detection, and the depth ambiguity is still far from solving. So the accuracies you saw, I think you didn't look into the numbers. Just a second, I'll just pull those numbers.
12% and all, yes.
Yeah, so this is still very small compared to LiDARs, which have like take a significant bit of processing. Their accuracies on the same data set, if you use the LiDAR data, that goes above 80. So this problem is far from solved. But this has its LiDAR comes with its own issues and challenges, and this is quite simplistic, and this is technically used as a LiDAR fallback method. So if the LiDAR fails, then you switch to the image-based method. So I would say like this problem is not solved yet. And the cross dataset generalization is also bad for these kind of problems. So there are like there's a this is very new problem, I would say. Like the work initially started with this ICCV 2019 paper, this one, and I think they have like almost around 150 papers have come out from that after that day. But I would say like it's still no one has got like an accuracy even close to stereo right now. People are still scratching the surface, doing this, that, and we are also trying some ideas. So yeah, so this is far from solving yet, and you cannot. The 2D object detection is very easily generalizable. You train it on Coco and just throw it in the wild. It does detect decent performance. But if you take a 3D object detector and throw it in the wild, it will not detect anything. So it is far from being solved, I would say. So I'm still looking into these problems right now. From
either LiDAR will become very easy processing, or either this will become very good. So any one of these things.
Yeah, I think people are slowly trying to like lessen the gap. But yes, I would say like.
Okay. I think Ashim has a question. Ashim, you can go ahead.
Yeah. Hi, Abhinav. So
yeah,
very
hi,
nice
Ashim.
talk. Yeah, very nice talk. So can you like briefly go over what are the evaluation metrics for on this Kitty data set?
Okay.
So you said IOU and AP, right? So can you like briefly explain what those are?
Okay. Yes. So I didn't explain this. So AP stands for like it's the same as like an average precision, and IOU is basically called an intersection over union. So unfortunately, I do not have a slide for IOU. Do I have? I just check. Oh no, I do not have a slide for.
So is that Jacquard?
Yeah, that's Jacquard in 3D. That's it. So the thresholds are actually like how much overlap do you see. So if it is greater than 0.7, it's considered a positive. If you have multiple boxes per a single object, that's considered a bad thing. So that metric will go down. If you also change the like the label of the object, for example, if you predict cars as a cyclist or cars as a pedestrian, AP will also penalize that as well. So it takes care into account the classification, basically what class, if it is the correct class or not. It also takes care into account whether it's it's localized well with respect to ground truth or not. And these two are just the thresholds, like what threshold to use. And these two are the most common ones.
Okay. Just another question. So regarding this data set, so does it have so we're talking about the diversity in the faces. So does this data set have diversity in terms of visibility? Like some of the images. I mean, basically the question is how does your model perform in low sort of visibility scenarios? Or
that's a pretty nice question. This data set it's an old data set, I would say. It was released, I think, in 2012 or 13. So it's like the very the most primitive and the most popular data set and benchmark. But it does contain limited variability. For example, there are no instances of cars going down the hill. So it's more or less like cars moving in the flat or sometimes moving over the bridge. That's it. And there are also less instances of or almost no instances of foggy weather or snowy weather. So there are more recent data sets have come up in past one and a half years. And the ones which I showed you in the beginning, this is from Waymo. So this is not the Kitty data set. I just showed you an example on Waymo. So this is more diverse and more realistic, I would say. And it's much more crowding as well. You could see there are much more dense traffic scenes in this data set.
And what is the fundamental difference between different evaluation splits that you have? So validation 1, 2, and test.
Okay.
I mean, do they differ in some particular characteristic or?
No, I think these are the splits. So the Kitty dataset, they do not release the test labels. You have to release it on, put it on their server to get the test results. And the full images is basically split into the validation. So if you add these two numbers, that becomes 7518.
I see. Okay. Thanks.
Oh, sorry. If you add these two numbers, this becomes 7481. Sorry. So this is the train and this is the test one.
Thanks.
Anyone else? Any questions? I think we have time. 3-4 minutes. No? Okay. Thanks everyone for attending the talk. Thanks Abhinav for this lovely presentation. And I think he's passionate about this and he sees there's lots of interesting problems yet to be solved in this area. And I think he's busy for the next 3 to 5 years minimum on this area. So thank everyone for attending and thanks Abhinav especially for
presenting. Thank you for the invitation. It was really nice seeing you all.
Yeah. So thanks for making us closer to self-driving cars that won't hit people. So as well. Yeah. So great talk. Nice work.
Yeah. Thank you.
Thank you. Bye.
Bye-bye.